I work in a group that is called A star, and is working on agents that act, see, talk, and reason. And in more details, the recent project I'm working on is embodied question and answering. So it's long-term task when we want to teach models, answer the question, navigate through the environment, your house, and answer a particular question, like where is it remote, TV remote, or what color of the car. And then you control the agent that is moving through the house and answer the question in natural language. So it's intersection of computer vision, NLP, reinforcement learning, navigation, and so on. So in this task, we use reinforcement learning to after we do supervision learning on frames that we captured, we use reinforcement learning to do fine-tuning and give a possibility to model to learn better the representation of the objects and the design of environment itself, so it knows and can interact with the environment by its own. Yeah, so let's talk more about reinforcement learning now. What type of deep learning and machine learning we already know? I'm sure you know supervision learning. You learn about that when we have labels to the data, and we try to teach model to predict that labels. Or unsupervised learning when we try to understand patterns and derive some clustering or structure for the data we provide to the model. And reinforcement learning is quite different from both of these, because here a model have ability to discover environment by its own. In this case, usually agent is controlled by model, and it interacts through the action with environments, and as a result, and in result of its action, environment returns state of the environment and reward. So reward is something that agent want to maximize, and the goal of the agent is accumulate the most of reward while doing actions. So that means that agent control the training data on their own. So your model is actually discovering the environment in its own fashion. Let's take a look at some examples of reinforcement learning problems. The most primitive one is cart pole. We control in this problem. Objective is to hold the pole on top of the cart and don't give it to fall down. While state of this environment is angle speed, position of the cart, and horizontal velocity. And we have control over the cart. We can increase and decrease the horizontal force of the cart. So then we will move the cart through this horizontal axis. And we get reward each time when pole is standing upright. So that means if it's going like 30 degrees down, we already lost. If it should be upright, and only then our environment continue interacting with us. Otherwise, it stop the episode and it say, okay, I'm done. So the goal of the agent is to hold this pole as long as possible. Like in the best case, like for 100 seconds, 100 steps. And then all these accumulated rewards, some of it will be the score of your model on this problem. Why I'm talking about this in details, because that's where most of our code and our implementations will be tried. So code that I shared, it works with this environment because it's fast to train. You can try to run that and attach that code to different environments, but it will take longer to train to see results. Yeah, so that's the toy problem. The more interesting one are the recent breakthrough in Atari games when OpenAI took a bunch of Atari games and said, okay, we have a model, and we give a model a possibility to do the action, actually to press the key in the game, and as the input model receives the RGB image of the game and the score. So that's it. Your agent have only the image and the score, and it should derive what to do to win the game. And it was very surprising that it actually built the reasoning what models should do and achieved human performance and achieve great results in terms of scores for these games. That's not so trivial to understand what's actually happening there. That's why reinforcement learning had a good sign that it can solve problems that were not solved by supervision learning. And after, I believe, simultaneously, AlphaGo was also solved by reinforcement learning. So when model won the champions in AlphaGo, in Go game, it was also powered by reinforcement learning. How many of you heard about Dota 2.5 model? Okay.
OpenAI?
OpenAI 5, yeah. So that's actually was powered by reinforcement learning as well. Of course, there was a number of secret sources from OpenAI that they added, but the main mechanism was reinforcement learning. And it started from this, it started from Atari games and continued to more complex environments. So the thing with Atari games is that OpenAI developed GIM library. Who is aware of GIM library? Okay, so the thing is that all these Atari games are wrapped into API. When you have an environment, you send an action and you receive a state of environment, reward, and if episode was finished or not. We will take a look on this in our code, but the main thing is that it was using this wrapper we can have an agnostic model that we connect to different environments, and it will be not specific for this environment. It can be pretty general, and we can scale it to any environment that follows this API. Let's go further. So another example is robotics. There is a big hope that with reinforcement learning we can teach robots to do stuff like parking, grabbing, and so on. How actually reinforcement learning is described mathematically? Markov decision process is the main model that is used for reinforcement learning, and all theory you have for Markov decision process is transferred to reinforcement learning. What is special about Markov decision process? First, it has states, the same as we described before, like our environments providing state. So the state can be how a screen looks like, or position of the card, or something like that. Then we have actions that agent can do. We have initial state from which all the process start. We have transition model to show which states are connected with which action. So if there is action A, it transfers from S to S dash. And we have reward function that describing how much reward we'll get with this action. And our goal is to maximize reward altogether in long run. And the important thing is policy. Policy is agent behavior. So for each state, we know the probability of particular action. So what does that mean? That means that our agent from this state can do several actions, and these actions are not deterministic. So for example, from here, with a 95% we can go to S1, and with 5% we go to S2. So that's important because this agent not always do the same action from the same state. It can be different. Let's talk about rewards and how they are described. We will go through the theory, and then we will have more entertaining format of cartoon, and which will describe the algorithm we are going to consider today. So stay tuned, don't be bored. So what types of rewards we have? First, like episode reward. After end step, episode finish, and if it was finished, then we get reward. Otherwise, if something failed, we don't have reward. It's pretty primitive reward. Another better one is additive reward, when you just sum all the rewards from each state through our path. And the last, the most commonly used reward is discounted reward. So it takes reward from recent state as the most important, and the future reward, like from next states, have discounted factor gamma here. So it's telling you that it's hard to predict reward from future steps. And that's why, for example, models usually optimize reward for 3-4 steps forward, and others are less important for them. Let's go further. And another important thing is value function. So value function is used to tell how potentially good is particular state. So it's estimation of how many reward we can get from this state, like limit. And so there is like mostly two ways to describe it. One is just like describe the state value, so expected return when you start from this state. Another is like state action value, like how what opportunity you have if you will take this action from particular state. Expected return if you will do this action. And there is to make an estimation of this value when we have policy P. So we have an agent that is following some particular strategy with policy. Then Bellman equation can help us to estimate their overall reward, and we try to optimize it. So that's the one way to calculate this value function. Yeah, so, and using particular state action function, there are algorithms that try to approximate it. And one of these powerful methods is Q-learning. We'll just have a brief look on that, and then we will go to algorithms that combine a little bit of Q-learning and other algorithms. So the thing is that it's tried to approximate Bellman equation with this kind of simplification. When we on the next step we try to find the action that is maximizing the future reward and subtracting current reward. We will not go into details for this particular method, but we'll go for another one that is pretty similar. So that's the formal definition of method we will discover, we will consider in details today. It's called asynchronous advantage actor and critic. We're actually going to dive into just advantage actor and critic, but the thing about asynchronous is that this is an algorithm that unlock opportunity to parallelize learning, reinforcement learning, and update the same model but by different agents. So that means that we can train our model in distributed fashion when agents are interacting with the environment, and then we collect all their knowledge that they gained and update one model. But again, we will talk about this later. I want you to focus on part that is just about one worker. I'm not expecting that you will understand everything here, because we will go again with more easy to understand definition of that, but at least to understand the parts that we will have. So first we assign our gradients to 0. We have two gradients. One gradient is for policy function, and one gradient is for value function. So we have kind of two approximations. One approximation for what actions we are going to take, and another approximation to make the right estimation of state. And then we have some policy, initial policy, P, and we try to update it with time. But first we collect the experience. We just sample the action from there and do the action with environment and collect the experience. After that, we assign rewards for each state using the sequence of states we went through. And in the end, we backpropagate two of these gradients based on actual returns that we have estimated and returns that we recalculated after we gathered all the experience. And we do this for a number of games, and then we stop. And then this is kind of train model. It's a brief description. We'll go into details now. So, yeah, the one interesting story about advanced Actor-Critic I found is actually a cartoon, and I asked for permission to use it here because I think it will be entertaining. So let's take a look, and we will have links with the code that we have in repo. So our agent will be Cranberry Fox. And Cranberry Fox, starting from some state in forest, and then Cranberry Fox decided where to go. It have different direction, and during their way from one state to another, they get the reward in terms of points of food. And what our algorithm is doing is try to provide with two outputs on each step. So first, it tries to create the estimation of particular state and how many reward we can receive from this state. So it calls critic. It tells like how good current state is. And for example, for this particular choice, then it will say, okay, it looks normal. I think I will get like 20 reward. It's based from like model prediction. It like assigned this number. And then there is another output from the model, from algorithm, so recommendation of what actual action to use. So this is a policy. And it says, here is a probability with which I advise to take each of action. And I don't know, there is more flowers here, let's go here with 80%, and the other choices will have 10%. And then we kind of sample the action, and depends on a random number, most probably A will be chosen here. Let's take a look on the model itself, how actually it's modeled. Can you tell me how many of you used Pytorch before? Okay, around 20%. How many of you used TensorFlow before? Okay, cool. Because all my examples will be in Pytorch, because Pytorch is obviously better. And I think it will be easy to build the analogy with TensorFlow, because it's pretty similar, I believe, in some cases. So the thing is, this is about model structure. We have input layer when we receive the description of the state. Then we have several fully connected layers that we learn. And then we have two heads for the model. One is policy, which actually have a number of outputs the same as a number of different actions. And we do softmax there, and it will be our probability spread. And we have value function here. It's just a float number that telling us how good current state is. So what is good about this model and why I chose this algorithm? Because it's modeled both of them. It's modeled value and policy. Why there is a number of different RL methods that concentrate on one of them. So Q-learning tried to work more with value, while policy gradient is working with policy. This algorithm optimizes both of them, and we will take a look why it's important. So here is the code. It's model definition in Pytorch. We will go through it and then move forward. You will find it in the code on the GitHub, and that's what we are going to use. So, yeah, let's go from the beginning. This is a model definition, like which layers we are going to use. First is like number of input layers is a vector with which we describe current state. And so it's constant, but it can vary from environment to environment. Then we have 64 layers neurons. It's fully connected layer. Then we have another fully connected layer. So it's 3 fully connected layers. And it's common for actor and critic. And after that, we have actor layer, as I mentioned. From the last layer, it connects to number of actions. And for value, for critic, it connects from the last layer of 64 to one output that is that will be the value of current state. And when we have forwards, when we push back when we push through the state, we calculate like all the linear things. We use ReLU as an activation function, so it makes this model more powerful and non-linear, so it can learn something interesting, not just a linear combination of weights and input. And then we have 2 functions to get the actual estimations. So self-x is running this forward function. So what does it do? When you ask about action probabilities, it takes your state x, it pushes through fully connected layers, and then it calculates action probability using softmax. And after softmax, we have like the spread of actions that in sum will give 1. And when we have one to state value is the same, we run it through our main model, and then we run in the head that just calculating the value, the state value. And we have both, we run like both heads. So this is model definition, doesn't have loss function definition and so on, but at least it will tell you how approximator looks like. Any questions here? You can ask any question.
What does exactly critic returns? Like probability or something like that?
Yeah, so you're asking about actor or critic? Critic return the estimation value for current state. So it means in this state, till the end of the day, how many reward I will receive. Why it's important? Because it tells you how potential this state is. And then when you receive a reward after your action, you can kind of compare it with your estimation from previous step, and that's why it's important. We will go through it next.
Is this prediction is for next action or all possible next actions that critic returns?
Action probabilities or
critic returns this.
So critic is for current state.
Yeah, critic tells you how much points you can get moving from this state now on through a lot of actions or only through.
Oh no, through a lot of actions. So this is a question like till the end of the game, till the end of the day. Like if I will move in this environment for whole episode, how much reward I will get. So if it's a Go game, it will tell you like what is the probability of win from or chess. Yeah, it's what probability to win from this state. So how potential this state of figures are.
The result, the implementation, how many layers or what kind of layers do the critic network and actor network do have at the end? So do they have three linear layers in front and the fully connected layer at the end?
Yes, so they have common part of model. These 3 fully connected layers is their common part. So here, so why it's important? Because when we have loss for value function and policy, they try to learn common thing together. So why? Because we have two heads, and then when we backprop the error here, we learn something common for both of these tasks. That's why it's important, because it's not two separate models, it's model that combine the knowledge through these three layers. And then actual value is just one layer, one fully connected layer from 64 to 1, and actor is actually the fully connected layer from 64 to n actions. So it's like pretty it cannot hold a lot of knowledge in this layer. All the knowledge is in these three fully connected layers. You can change this with another models like LSTMs and so on, so it's not something that is required by algorithm. It's just some model that we use here. So let's go forward. So our folks decided to go and take an action and receive a score. And then what Fox is doing, it's logging all the states. It's logging what was the prediction in current state. So what was Fox thinking about current state? Then it's logging action, what was taken, and reward that it receives after it chose this action. And it repeats it again and again. There can be the case where all the actions are pretty similar, so there is no strong correspondence that one action will bring you more reward. But I want to take a look that you have some signs here that can potentially tell you that there is a reward on C, but our Fox doesn't know that yet. So she takes an action, C, and get a lot of reward, and then it logs it. It logs the observation that it gives plus 20 action C, and then it do it again and again. So how does it look in code? Because cartoons are good, but code is better, right? Let's take a look. So it's pretty general loop for most of reinforcement learning cases when you use gym. So environment here is actually a gym environment. So it has the same method like reset, it has step, and I believe that's it. Yeah, that's all we need here. So what is happening here? We are running the next procedure for endgames. Endgames is actually correspond with a day or episode. So it's like separate episode when we finish the game and went to the final state. And then the thing is that we gather the training data for smaller end steps. So we are not running to the end of the episode, we're running only for, I don't know, 20 steps, 5 steps. What we do here, we wrap state S in variable for Pytorch to do the backpropagation for this variable. Then we take action probabilities from our model. It was initialized with some random init weights, so it's not so smart yet. So it's give us some probabilities. Then we take a sample from these probabilities. So multinomial number of sample is 1. So we take this like probability thread and say, please generate one action for us using this probability for each action. And then we have we do a step, and the environment return us next things. Next step, reward, and if its episode is finished or not. I don't know if somebody knows Jim. Somebody knows what is that, but it's not so important. It's like some additional stuff can be passed through this. It's info. People sometimes put additional stuff there to get for their models. But the most important part is reward, next state, and if it's finished or not. And then we just log everything as Fox did. We capture states, we capture actions, we capture rewards. And we do that again and again, and then after end step ends, we will reflect and learn our model. So after collecting the observation, Fox is reflecting on the experience it gains and try to improve her model. and tune it. How does it work? Because actually, our fox was moving only for several steps, and it never reached the end of the day. So it's never went to the end and know the actual value for a particular state. But it's still not the problem to improve results. So the thing is that if our fox did 3 actions, 1, 2, 3, and stopped, and then it have value estimation here, and it can calculate value estimation here plus this action. Is it this value estimation here plus this action? Is it the same as value estimation here? So it have already the data to improve it its value function. We'll see it. One note is that we use, as I mentioned before, we use a discounted reward. So some reward on next step is more important than reward in the end, because there is a probability that we will never get that reward if we will choose another action. So that's why we use discounted reward here. So let's take a look how error is calculated and how backpropagation is done. So as I mentioned before, we have a last state. We know the estimation for this last state. And then we take previous reward and check and fill it as a value state that we want to have for this state. But this is our estimation, and we'll see that it's 2 points off. So we have error here corresponding to the last state. And the same here, we do the same thing. We received 20 reward, our estimation was 19, but actually it's 40 because it was 20 plus 20 is 40, but our estimation was 90, so let's have an error. And then we have all these errors, and we want to use that to improve our value function prediction. Any questions here? Discount? It's hyperparameter, so it's actually constant. So here is a code for that just was mentioned, like calculating this reward, this right value function, kind of right true value function, and backpropagating the error. So what we have rewards, and we have if it was last state or not. We do reverse for rewards and downs. Why that's important? Because we are moving from the back, so we're propagating it from the end of the list, as you saw. Then we handle end of episodes. Each time we have an end of episode, it means that reward value function in that state is 0. Because we already finished this episode, and there is nothing we can gain in the end of the day, because we already this state is potentially 0 for us. And then after that, what we do prediction. So we get state value function for current state, and we do it only for the last state in current states. So we do it only for this state. All other things we calculate based on that. So yeah, here we go. We use the reward from previous. We use the reward from previous step, and yeah, we add it's reward from previous step. It multiplied by gamma discount factor, and we add current reward. And that's how we calculate the same rows that we did on previous slide. After that, we return it, and then it will be used by learning function to create a loss. So reflect here is actually like training method. So we get these states. We after that calculate for this state that we have. We calculate action probabilities and value estimations. Then we calculate log action probability. That's important because we want to have entropy as well. And calculate the loss for action part of model. After that, we take actions, wrap it into Pytorch variable, and get log probabilities for action that was chosen during the way. So for that particular action that our fox took on the way. So this is for these actions we calculate log probability because we want to know how likely was that actions. Because if they are good, we want to use that in our backpropagation for error. So then we will talk about this on other slides as well. So I think we will cover it additionally. Then we calculate advantage. Advantage is a difference between current estimation and actual true value. So it's our error. How bad was our estimation compared to true state on current step? Then we calculate entropy of actions that we take. Entropy is probability of action multiplied by log probability of that action. So it shows how spread it was the actions for particular move, for particular state. And then we calculate action gains. That's why we have an advantage, what we received based on this action. And then we use log probability of chosen action. That's what I told you. We want to punish more that actions that were more likely, or reward more for actions that were more likely. And then we have value loss. It's calculated actually as advantages, square root of advantages. And total loss is combined of value loss, action gain, action loss. So action gain is opposite to action loss. And then we have small factor to include entropy as well. So we want to promote discovery for our model. So we want our fox to take different actions, not to fall into one action and use only this action and don't discover other scenarios. We will talk. We have slides for that as well. By the way, what is okay? Small break. So 1 second. When we finish in 30 minutes, something like that. Yeah. Yeah. Let's take a small break because I think speed after the break will be faster because we need to take a look on the implementations and the actual demo. 5 minutes break. Okay, let's continue. We'll move a little bit faster, so then we have more time to spend on demo and laugh from the results of reinforcement learning in the end. Okay. So, and Cranberry it repeats the same process again and again, and reflecting on them, so it's learning from time to time. The thing is that, yes? So the thing is that that's good when we have one agent, but it's pretty slow. Let's imagine that we have a number of foxes, and all of them use the same model and to go through the environment and calculate the error and rewards. And then they update one model with all the experience they gain. Then, first, the good thing is that they mixed a lot of different not correlated samples and experiences. And the another good thing is that we have much more experience. It's more stable to train on the larger batches of training data. So that's why asynchronous part start working. So we have them working separately, and we can then aggregate all the experience and do it in distributed manner. So the day is almost over, but the day is almost over, and earlier we have for each action we have a probability of confidence in this action, and On this slide, we want to show once again that we are not taking just the best action here. We're taking the action with some probability, and we sample from that probabilities. Because why it's important? Because we can discover some new actions that doesn't give us reward immediately. So, for example, here we see that C direction is pretty looks not so nice for our fox and looks dangerous, but there is still good probability that fox will take it, and it take it, and maybe it will be exciting. It will give more reward, but it can be an opposite. So that's about entropy. On the left we have low entropy, on the right we have high entropy. So it's spread, probability spread across actions, and we want things on the right more, because we want fox to discover more states and check the environment and discover some hidden games. That is reflected in our loss function. We have entropy here. So looks like gamble paid off, or did it? And if it's not so good, for example, we went in bad state, and that's why important to have value and policy together. So we are in the state where our estimation is -100, so it's bad state already. And then we will go and our fox choose one action and lose -20. And fox want to adjust her inner actor and to make better choices. So what is different compared to other algorithms? If you have like just policy gradient fox that is optimizing policy, like action that brings more value, then in this case we will consider this as a bad action. Why? Because it brings us -20. It's a bad action. It doesn't increase reward. But in our case, as we have value functions that is -100, it means that -20 is not so bad, because we are already in bad state, and we can relative improvement is around 80, and that's kind of a good thing to have. And that's why this particular action is good, while for us, but maybe not so good for other algorithms. Yeah, so the difference is that actor is use advantage, like how many we can receive using this action, and the critic is using an error, so we try to improve improve error and decrease it with each step. So after some time, Fox and her actions became more fine-grained, and probability of good actions will increase, and her choices and surprises will be less often. So our value function will be pretty the same as estimation. For that case, we have like evaluation. So imagine we want to evaluate trained model. Who can tell me what is different here compared to gathering the experience? So when we run model just to gather experience, and when we do the evaluation of the model, what is different? Who can highlight the things?
We do not backpropagate.
We don't backpropagate, but in gathering experience, we don't do backpropagate as well. We don't change our model. We do it during reflection. Yeah. So here we also run our fox through the environment. So we have an environment and we do the action, but something is different here. So yeah, it can be hard to find it, but the thing is that here we just take action probabilities and we take max of action probabilities. So we don't have any more stochastic things. It became deterministic. It always pick up the max probability because we want to perform the best during our testing. When during training we are interested in discovering different trajectories, during estimation we want to win. We want to show best results. So that's why we don't have sampling, we just have max here when we choose the action. Okay? So Preparing the workshop, I trained the policy grading a little bit different algorithm for ping pong. So the thing is that model see this image and know the score. It was optimized to increase the score compared to bot 2. And let's see how it looks like. So after 1 day of training on my laptop, it hit the ball sometimes, that's very good, but it still cannot win any game from 20 in a row. After 2 days of training, it was trained with reinforcement learning, so it was just playing all the day this ping pong game, gathering the reward from the games and improving the model and so on. And yeah, it won first point. 2 days. Okay, more. Yeah, so average was like 3 points compared to 20 for the algorithm that was coded by authors of the game. And then I found already trained model by someone else. It was actually, I think, asynchronous model. And yeah, it looks pretty decent. So the algorithm that we just discussed was used here. And yeah, I'm not sure I could win against this model. I don't know the time and how long it will take on my laptop, but from what I know, if you have 8 GPUs, you can train it for 1 day easily. Okay, so we can take a look on code that I have here, and I will run it, and then we'll talk a little bit more about RL in the real world. This is a code that we have in repo. So what's happening here is try to gather the experience for that's working the model that we just saw on the slide. So that's that code with a policy and value and 3 fully connected layers. As I mentioned before, episode ends when angle reach 30%. So now it looks very bad. You just start playing and lose immediately. Okay, it's a little bit better because it starts moving a little bit further. Yeah, so after, I will leave it to train. Yeah, so the bad thing I saw, it was for some cases it could hold this pole for a long time, but mostly it just pushes it to the right and it takes around 100 of steps. So it holds it for 100 of steps, which is already kind of good for short training time.
Which file is it?
It's a notebook tutorial. So yeah, it's this A to C and steps tutorial by. And then, so let's go back to the presentation. Let's talk a little bit about RL in real world, because it has a lot of critics before, like hey, it's not so good and not so controlled as supervised learning, so something can go wrong with reinforcement learning and you don't have a control over it, but it still make reasonable breakthrough in numbers of different directions. So one is like traffic light control, robotics we already have a talk, web systems when we have parameters that we need to adopt and any like full brute force search will not work. Reinforcement learning can help you to adapt it to the situation. Chemistry, it was also used to find the right portion of elements to get the best reward. Personalized recommendations when you have a number of people and you need to you need to have a particular recommendation that is good for this person, and you have reward in terms of clicks or some interest with your recommendation. One book I could advise you to take a look is a RL intro book, and this is like the first thing you should read about that. It's like the Bible of reinforcement learning, and then all like latest papers will be a good plus to get more knowledge about that topic. I'm open for your questions and any discussions that you're interested in.
Sorry, does your code work well in your laptop? Because there are some problems with...
One second.
Does it work well on your laptop? Because there are some problems like this.
Yeah, let's take a look. I will help you to run it if there is a problem. I think I can update with recent version I have. There is some inconsistency in terms of Pytorch version. I believe that's important. Which Pytorch version are you using? So yeah, let's catch up on that. One, two, three.
Can you shortly describe what's inside of repositories and how we can continue learning?
Yeah, so the thing about repo was that there are implementation of this algorithm, like production implementation of this algorithm that working faster, asynchronous, parallelized, and so on. In this repo we have simple implementation that's kind of possible to consume and read and understand. Yeah, let's take a look. So there is two main folders. One is A2C, so it's without parallelization, and A3C with parallelization. So without parallelization, this is notebooks. First are for Monte Carlo part, so just showing how without any model, just on counting statistics, you can still train a policy for your model and policy for your task. So you just count the reward, running a lot of experience gathering and accumulate reward for each state, and that's what's happening in these notebooks. Then step tutorial is actually the code that we look through, and that is training this carpol without parallelization. And then these are modifications. The last one is using pixel input instead of state description with the position and angle. The parallelization is added as well here in some of them. And yeah, so most I think is that it's evolving from simple to more sophisticated one. And in this simple asynchronous 3C is again easy implementation of first discrete A3C. When we have environment, when we have like action, discrete number of actions like 5, 10 or something like that. In continuous, we have a value that we need to specify, and we can choose it continuously. It can be anything from 0 to 1, and that's a little bit different approach and a little bit different. Approach is the same, structure of the model is a little bit different, and the way how we gather the reward, I believe, is also different. Yeah, that's it. It have part with the parallelization, so you will see worker here that is a process itself, and it's running the same thing we discussed, like getting the experience separately, creating a buffer, and then there is a synchronous push and pull for models, so they updated the same model and using Pytorch distributed to share the model between a lot of workers. So that's main interesting part compared to something we already took a look. And continuous is totally the same code, but for continuous one. So it have different structure a little bit, and I believe that's mostly it. Yeah, so what I would advise to try, first to run it, then try to improve the results. So try to add additional layer, try to change the learning rate, try to make it more stable, and try to output reward during the training to have more control of how actually the model is trained. You will take a look that it's not training the same way as supervision model trained. So in supervision, it's like our validation loss look like that. It's improving, then it's have a maxima and then go down, and it's overfitting when it's go down, but training loss is, it's opposite, because loss is opposite. So it's high, it's go down, and then it's go up again. So it's overfitting because it's not improving if you will wait for too long. And for reinforcement learning, also start from the bad state and then it improve, but after that it can be really unstable and go into a very bad state in the end. Why? Because your model is controlling the episode that it's training. So it's controlling training data. And when you run the reinforcement learning with different random seeds, you can receive different results. Because sometimes it can be not stable and go into wrong direction just because your model is exploring the environment and it can explore it differently with a different random seed, for example. So reinforcement learning is definitely less stable than supervised learning.
Could you possibly maybe update requirements to try to install from scratch to know?
Okay. Update the requirements to make sure that it works for both. I think I will do, but I think it's not about requirements, it's about that some notebook is using old Pytorch. So I will change the notebook then. So you will have a code that is running, I will send it to the repo as well. Okay. Yeah, so feel free to ask questions here. I'll be here for several minutes. Thank you.